Hey, so I sent out an email this morning. Hopefully you all at least received it. Email's complicated here. Two things that I've now put on Wiley Plus. One is the first problem set. It's actually up. You can complete the questions. You can at least look at the questions. You can answer them only once, but you can look at them as often as you like. And I encourage you to look at them in advance and start thinking about them. And you can talk about them among yourselves. Don't farm out the work, because you end up defeating the purpose for yourself. Because part of this is preparation for the exams. If you don't do the questions yourself, you won't be ready for the exams, and it'll not be good. So anyway, look at the problem set. I'm happy to talk with you about questions. My office hours Monday afternoons, Wednesday mornings. What else? There's 16 questions. They're all about the physics of this first chapter. Through what I'll talk about today, I might manage to get through everything you need today. We'll see. So it should be available on Wiley Plus under the assignments or visible, and there are a bunch of panels. You should be able to find those assignments pretty easily. The other thing that I've assigned are all the chapters 1, 2, 10 through 15 of Orion questions. These are just practice questions. And they're graded differently, and they contribute to a different thing. They're not homework. They end up in this online reading and practice piece. It's just a little piece of the semester score, 10%. But I just want you to just keep picking away at questions and challenging yourself with those. The way Orion works is it asks you to do a diagnostic before it gives you what it considers the Orion questions. The diagnostic is kind of a nuisance. I can't turn it off. Their questions are okay too. Except for chapter 1. The diagnostic questions for chapter 1 are anomalously quantitative. They're all calculations. I hate them. I can't get rid of them. You're welcome to dismiss the diagnostic. It doesn't count towards the questions. It's just a preliminary. So there's a little circle, a red circle with an X in it. You can just press that button and it says, "Do you really want to do this? Are you crazy?" And you can say, "Yeah." And that will just take you right on the Orion questions and skip the diagnosis. Otherwise, if they're useful to you, they're useful to you. So answering more questions is better than answering less, as long as they're accurate questions. Not all the questions on the site are perfect. That's another issue. But okay, so the homework is the homework. It's really graded. The Orion, it's not. It's threshold based. If you get more than 60% on this score, according to its scoring scheme, which is a little complex, you get full credit for it. So it's not meant to be like tear your hair out over every question. It's meant not to be like click, 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 click. There have been people in the past who did that. That was a waste of time. It's meant to get you thinking. Any questions about the assignment, problem set 1, and Orion, those questions? The problem set 1 is due Wednesday at the start of class. The Orion, I just made it due right before the final exam, because when those questions will be useful to you will depend on they're probably particularly useful right before exams, like in studying for the final. So I made them due at the end. You can put it off for as long as you like, but that may not be the proper choice. All right. So on to the content again. I was talking about ramps, and so far we haven't had a ramp in front of us yet. I mean, it's going to be this. There's the ramp, but just to start off, let's leave the ramp flat and just look at the interaction between a wagon, say with a blocky kid in it. Sit still, Tommy. What are the forces going on here? And the forces are. Now, there are two forces acting on that composite wagon. I'll stop worrying about whether there's a kid in it or not. Just the wagon. The wagon's got its weight downward. That's evidently balanced by some upward force. It happens to be upward force exerted by the sidewalk on the wagon. And it's not a gravitational force, so it's not weight. That force is a support force, just to give it a name. And again, you may have learned that same force under other names, normal force and contact force, are common. So it's an upward force in this case that the sidewalk exerts on the wagon perfectly balances away the wagon's weight. As a result, the net force in the wagon is 0, and it's not accelerating. The hallmark of experiencing 0 net force is no acceleration. All right? Well, I kind of finish up with the idea of, well, how does the sidewalk, what makes it so clever that it knows just how hard to push on the wagon? And associated with this is, are there ever circumstances when the sidewalk can push either too hard or too soft on the wagon? And the answer to those last two questions is yes. The sidewalk isn't clever in any respect. It's just, it does figure out how hard to push up on the wagon, but it's a negotiation process that leads to that. And to let you see the negotiation, I went over here to this scale. And again, the spring scale's behavior is that it tells you how hard it's pushing up on whatever's on top of it. So right now it's pushing 10 units up. The units happen to be newtons. Now it's pushing 50 units up, 80 units up, 100 units up. So if I put the wagon on there and I let everything settle down, so I hide the story, I hide the negotiation, and we come back, negotiation's all done, it's pushing up with just short of 60 newtons of upward force on the wagon, which turns out to be the weight of that wagon right now. The wagon weighs 60 newtons down, the scale is pushing 60 newtons up, they sum to 0. Perfect. But during the negotiation, it was all over the place. And the physics of that negotiation, which, okay, it takes place on the scale in a kind of visible manner. You can see the scale going up and down, the wagon bouncing. Can you see the wagons going up and down? I could play with the television and you could watch it up close, but it's you can imagine it's bouncing up and down. This is the same negotiation that occurs when you get on a trampoline surface and you settle down. Any of those flexible, pliable surfaces will do this. And the idea is this. At this particular height on this springy surface, the springy surface is pushing just hard enough to support the weight of the wagon. And the wagon's experiencing 0 net force. That situation of experiencing 0 net force is known as equilibrium. There are a couple different equilibria in physics and sciences. This is one of the most important types of equilibrium. It's a mechanical, I guess, equilibrium, where there's no net force. And it's a position in this case. This is the equilibrium position of that wagon. It's perfectly supported here. Right? If the wagon were a little lower, it would be squishing the spring scale more. And the spring scale's behavior is to push back harder. If you shove it down extra hard, you're pushing on a spring. And the spring will fight you harder. And the result will be that the upward force exerted on the wagon is more than the wagon's weight in the opposite direction. So the wagon's not 0 net force. It's not at equilibrium anymore. So if I shove it down, I went all the way past there, it's 100. The scale's pushing up with 100 newtons. And we know that the wagon's weight's only 60. If I take my hand off, that wagon's going to experience an overall force, a net force, of 40 up. That's the difference between 60 down, 100 up, 40 up. Okay? And if I let go, woo! The first thing it does, it starts accelerating upward. Because it's overall it's pushed up it goes. I mean, I got to be careful because I don't want to confuse acceleration from velocity. Just because it's accelerating upward doesn't necessarily mean it's going upward. But if you wait a little bit, it's going to be going upward. Acceleration is the change of velocity, so it's got to accumulate upward. So but whenever it's below equilibrium, the main point is, whenever it's below equilibrium, it's being pushed super hard, harder than its own weight. And it will therefore have a net force up, and it will accelerate upward. That's, at its basic. Okay? If it's above equilibrium, the scale isn't squished very much. It doesn't push very hard, the spring. And so the wagon is under-supported. It actually weighs more than the spring is pushing up. And so the net force is down. So the characteristic of this situation, where you've got a springy thingy, sorry, accident. Sometimes my clowny remarks are accidental. Sometimes they're on purpose. You can laugh either at me or with me. So at equilibrium, it's perfectly supported. Whenever it's above equilibrium, it's under-supported and tends to accelerate downward. Whenever it's below equilibrium, it's over-supported and tends to accelerate upward. And that bouncing motion, is it trying up? It goes too low and it accelerates upward, and pretty soon it's moving upward. And then it gets too high because it sort of overshoots equilibrium. And now it's under-supported and accelerates downward, and then so it's trying all the possibilities. And it's continuously accelerating back towards equilibrium. Whenever it's above, it's going down toward equilibrium. Whenever it's below, it's accelerating up, back toward equilibrium. It's trying to go to equilibrium. But when it gets to equilibrium each time, it is moving. And although its net force on it is 0, because it's at equilibrium, it doesn't mean it's motionless. That just means that it's not accelerating there. And if it happened to be heading upward when it reaches equilibrium, it's going to keep going, because right at equilibrium, it's inertial, and it follows inertia. It keeps going upward. So it's hunting, trying desperately to settle at equilibrium if it can. In the settling process, which is something I talk about more in the fall course, the settling process involves getting rid of an important physical quantity that we're going to learn today, known as energy. I mean, you know energy to an extent. And that bouncing motion involves energy, and it can't settle until it gets rid of the extra energy that it has associated with that bouncing motion. So it's actually that motion is super important in physics and in life in general. It's the motion of so many things. That bouncing motion is, my favorite example is it's the motion of most musical instruments. You know, what's vibrating back and forth? The strings on a guitar. It's that same exact bouncing motion. The Ruffner Bridge. You go over there, probably at some point during your career here, you've played bouncy. Yeah. So in my example, it's not a sidewalk. Does the sidewalk bounce too? The answer is yes. There is no such thing as a rigid object in the sense that it has absolutely no movement or bending. These are these inconsistent, impossible things, immovable objects, irresistible forces and stuff. Everything bends to some extent when you push on it. So if you push on a sidewalk, it dents a little bit, unavoidably. The whole process of trying to create the support force, of avoiding the overlap of atoms and molecules, well, they don't totally avoid overlapping. They begin to overlap, and that summons up the support force. So everything flexes a little bit. And actually, the Ruffner Bridge, which I was starting to go on about, is a nice example because it's pretty seriously rigid. Except if you get a bunch of people on there, and everybody goes, jump, jump, jump. What you're doing is you're trying to pump it up and down at its natural rhythm. Things do have natural rhythms. This you can see the rhythm. Bounce, bounce. That's got for good physical reasons. If you do the same thing with a bridge, you'll get this seemingly rigid object to bounce up and down. And sidewalks dent, everything dents a little bit. It's a question of just how much. I mean, if this were a diamond table here, and we put the wagon on it, it would dent a little bit. Then we'd rush off to the bank to put it in a safe deposit box. Is that okay? So the negotiation that you see here on a grand scale with a bouncy spring or a trampoline is happening anyway on the sidewalk. It's just not so obvious. There's a little bit of bouncing there that's going on. And then it's negotiating. It now has settled at equilibrium. But during the settling process, there were times when the sidewalk pushed too hard, pushed too soft, pushed too hard, pushed too soft, a whole bouncing process. And that was, so remember I asked early on the question about, I used to have a bowling ball up here, where I said, can the bowling ball ever push on the table with a force greater than its own weight? And we all decided, yeah, it can. How do you do that? Drop it. Because when you drop it, you're making it go through that negotiation process. And in that negotiation process, it will have times when it has dented too deeply and is being pushed up extra hard, and when it's dented too little and is being pushed up too weakly to be supported. So it's going back and forth. And the size of those excursions above and below the equilibrium depend on how much you whack it in there. So if I had taken this toy here and dropped it on the scale, it would hit very hard. It would break the scale, right? It would go way past anything the scale could deal with. And the same thing happens on the table. Other questions? Thanks for asking a question. Okay. Yeah, it's Friday. It's the middle of the weekend, right? So it's hard to ask questions. I've watched the weekend drifting forward. I think I would say by the end of my career, but who knows? You'll have Monday classes. Maybe not even that. Monday morning. No, not morning. Monday, whatever your favorite, 11 o'clock. Okay. And only for 15 minutes. All right. So, a little bit about, I've been kind of cavalier about talking about the sidewalk pushing on the wagon pushing on the sidewalk. I've been flitting back and forth between those two things. Are there two forces? Are they related? Well, yeah, the answer is yes and yes. And so just a question to ask you here. If you push on a friend, or a former friend, is there any case in which your friend will not push back on you? You okay with the question? So they're texting away or they're asleep. How many think that, yes, there are cases when the friend will not push back? How many think no, there are no cases? Great, you guys got it. Yeah, this is the action-reaction concept that you've heard tell about all these years. When you push on something, it pushes back on you equally hard in the opposite direction every time. And I can't underemphasize something like that. The extent to which this is true. This is so true. There are times, and I'll try to bring them up, where you think, well, no, it can't be pushing back as hard. The answer is, it's still pushing back equally hard. Doesn't matter what the two things are doing. It doesn't matter whether they're awake or asleep, any of that. They always push back. And that is known as Newton's third law of motion. So it's the last of the Newton's laws. And it says that if object A pushes on object B, then object B for sure pushes back on object A equally hard. So the forces have the same amount, technically known as the same magnitude, but their directions are exactly opposite. So, and you okay with that observation? Yeah. So the question here is, if you push on the wall's not going to push back on you. What do you think? Does the wall push on you when you push on the wall? Yeah, it does. And I can show you that it does. So I'm going to get rid of friction by do not stand, okay? Do not follow instructions, okay? So I'm inertial right now, no net force on me. So I'm motionless and staying motionless. To begin moving, something's got to exert a force on me. And I'm pretty well frictionless here. To get a force, something to push on me, I'm going to get the wall to do it. So I'm going to push the wall to your right. And what do you think the wall's going to do to me? It pushes back. It's going to push me to your left. So that's how I got myself moving. This is a perfect question. If they're equal in magnitude, the two forces are equal in magnitude, opposite in direction, don't they cancel? You all okay with that question, that concern? It is the great concern with Newton's third law. That is everyone struggles with this a bit. The observation is this, how many forces did I experience when I pushed on that wall? There were two forces. I did push on the wall, and the wall pushed on me. How many of those forces were acting on me? How many think there were two forces acting on me? How many think there was one force acting on me? Good, only one force. So the net force on me was only the wall's force on me, right? There's a vertical stuff going on, but it's all canceled. So I was only experiencing one force, and it made me accelerate. How many forces was the wall experiencing? How many think two? How many think one? Just one, right? That affected the wall. So the point of this is, I'm here in treacherous land, that whenever forces always come in pairs, and I call them Newton's third law pairs often enough. They always come as a twofer. But those forces never cancel without exception. They never cancel because they're never on the same object. They're always on two different objects. And if you can get that, that's hard. Believe me, this one, maybe I feel like I've said this now as cleanly as I've ever said it, but it's one that lingers with people. That Newton's third law, that two forces, they're equal and opposite, don't they sum to zero? Well, if you sum them to zero, yes, they would sum to zero. That's true. But because they're on different objects, there's no meaning to summing them to zero. It serves no purpose. It would be like, I don't know, it's like adding the money in this bank and the money in your pocket. Yeah, you can do that, but it doesn't tell you anything interesting. So when I push on the wall pushes on me, I accelerate. As a result, what do you think the wall does? I did push on the wall, for real. What do you think the wall did? How many think it accelerated? It did, right? Why didn't you notice it? I mean, apart from the fact that you're sort of attached to it by way of the seating and stuff. How about the mass of what I pushed on? The effective mass of that wall, because it's attached to the whole Earth, was fantastic. And so I pushed on it, and that would make it accelerate. But its mass is so huge, the acceleration was tiny. So, yeah, what we can do, if I want to do this. Yeah, it's Friday. And 2 volunteers who are willing to stand on these carts, or at least kneel on them. Please. One other person? Jay, yeah. All right. No injuries here. Okay, first off, without the carts, you can push on each other. You hold the frame, and is there ever a case where you're not pushing equally? This scale is reading how hard, your name? Matthias and Jay are going to push on each other by way of the scales. Matthias' scale will tell you how hard he's pushing on Jay, and Jay's scale will tell you how hard Jay is pushing on Matthias. Is there ever a case, no matter what you do, when you don't push equally hard on each other? I mean, just try. Okay? Right? I mean, it's a little goofy. Okay, I'll stop and stop embarrassing the two of them. But no, you can never do it. And this includes when you're accelerating. And so the idea here is, if you guys can do it, stand on these two things and push on each other. You probably want to stand, rotate 90 degrees so that you side. And now as you push, watch, they will both accelerate. The forces were equal and opposite, but they both accelerated, and you guys have pretty similar masses despite slightly different geometries. What's the weather up there? Sorry. He'd never heard that joke before, never. Sorry. Thanks, Jay. Yeah. So, but you can see they both accelerate apart because how many forces did Jay experience? And Matthias experienced how many? 1. Never cancel. Is that okay? Yeah. Thanks, guys. All right. So when you push on stuff, it pushes back. If those forces are not canceled by some other effect, like if they were standing on the ground pushing on each other, you wouldn't be able to see the influence of each other's forces because they would experience other forces by way of friction with the ground, which would just like wipe out the fun. But two objects that are free of other forces and simply push on each other, they're going to accelerate apart. And their accelerations will be inversely proportional to their respective masses. So the most massive thing, like the wall, it's going to accelerate, but not enough that you notice. Okay? Question, fun fact, an expression I don't use, but I use it just now anyway. As a kid, I was like, there were these issues that came up like, Dad, is it true that, or is it, anyway, when you jump like that, okay, does the earth move? And I asked this question at some point or other, and I'm not sure my dad knew the answer at the time. But the answer is, so this is preparation for you all, yes, the earth does. When it pushes up on you to make you accelerate upward, you push down on it to make it accelerate downward. And it does accelerate downward. It's just so small that it's essentially imperceptible. Furthermore, there are other issues like the earth, the floor, the earth, they're not undentable. They dent a little bit. So they got that negotiation trick going on, which makes life a little more complicated. So it's still, the earth really does accelerate downward. Okay? All right. Insight, gravity belongs in this story too, because when you jump upward like this, the earth is accelerating downward as you're accelerating upward. Nah, during the jump. Afterwards, after you lose contact with one another, which way are you? Are you accelerating once you've lost touch with the ground? Downward. Right? That's a force. What's the other part of the Newton's third law pair? Because every force is always come in pairs. What do you think you're exerting on the earth while you're above the ground? You're pulling up on the earth with a gravitational force. It pulls on you, you pull back. Nobody ever notices this it's immeasurably hard to find this effect. But if it pulls you down with a force equal to your weight, you pull up on it with a force equal to your weight, but in the upward direction. It's real. That is actually there. That's the Newton's third law pair. It has such negligible, noticeable effect on the earth that you wouldn't notice it. The earth and the moon, however, do pull quite strongly on each other. The moon's kind of big, and they are pulling out. The earth whips the moon's motion into a circle, sort of. It's an oversimplification to say it's the moon orbits the earth, right? Well, it's a little more complicated than that because the earth is pulling down the moon with gravity, but the moon is pulling up on the earth with gravity, and they're actually doing. If I had another person up here, we could swing around each other, right, in a sort of a circle. But imagine that instead of it being two sort of equal people, it's one gigantic person and a little tiny child going around. And the child does most of the whipping, but the huge person does a little bit. And that's what's going on with the earth and the moon. They're actually going around each other. The earth barely moves noticeably, but it kind of wobbles as the earth goes around it. All right? Lost in space here. What else? Oh, well, this is one, and we could have done this while Matthias and Jay were up here, but this is one of the classic things that leads to misconceptions or torments people about Newton's third law. If you push on a friend who is moving away from you, compare the force you exert on your friend to the force your friend exerts on you. How many think that if I push on somebody who's going away from me, that I push harder on them than they push back on me? How about they push harder on me than I push back on them? How about we push equally hard on each other? Good. You got it right. There are all these situations where you think like, if you push on a passing rocket ship, whoosh, you exert a 1 Newton force on it. Will it exert a 1 Newton force back on you? Yes, it will. It doesn't matter that it's moving by at some crazy speed. It doesn't matter. Okay, I'll stop with that story. This is exactly John's question about the two forces potentially canceling in a Newton's third law pair. They never cancel because they're never acting on the same object. Okay? And if you get that straight, you're really a big step ahead. It's not trivial to get that one and to believe it and to hold it in your head. Think of it again in a week and convince yourself again. Newton's third law pairs never cancel, never sum to zero, because that's never a useful activity to do. All right. Oh, we did this one. Oh, well, I can do another version of it. Well, yeah. It's the next question. So, can a ball ever push downward on a horizontal table with the force greater than the ball's weight? Yes. I'm sorry. Yes. 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 Okay. And the next version of the question is: can a table ever push upward on a water balloon with a force greater than the balloon's weight? How many think yes? Fine. Because they go hand in hand. During that negotiation process, if a ball is pushing down on the table super hard, the table's pushing up on the ball super hard. Same with the water balloon. So there's a water balloon experiencing, I'll settle it in at equilibrium. I did the negotiation quietly behind my hand, and there it is. It's perfectly supported. But when I first put it down, it's doing that negotiation. And if the negotiation is too extreme, it can't take it. I can't take it anymore. All right. Before I kill myself. I'm committed, but not that committed. Maybe I should be committed. So, with that all now, we can start looking at a ramp. And to make the ramp a ramp, I'm just going to put a block under it. There we go. So now it's a ramp. And if I put the wagon on the ramp, it no longer is net force zero. There's no equilibrium available to it anymore. The observation is this: it always accelerates downhill. You've never seen something accelerate spontaneously up a hill. It's always downhill. And where does that come from? Well, it comes from a failed cancellation of the support force and weight. When the ramp was flat, when it was a sidewalk, weight was straight down, and the support force being, as it always is, perpendicular to the sidewalk, the support force was straight up, the weight and the support force could cancel because they're in exactly opposite directions. The sidewalk pushed straight up on the wagon, great. Okay? But once we tilt the ramp, the support force is not being exerted by a horizontal surface. It's being exerted by a tilted surface. That support force is up at an angle, as I got drawn here. And those two forces, weight down and support force up and to the right, they can't cancel. They can do their best. And what they do is the negotiation that occurs still is just so that the wagon does not dent, does not penetrate into the ramp surface, nor does it leave the ramp's surface. The negotiation occurs along the direction of the support force until everything's settled there. But that doesn't cancel all of the weight. These two forces just don't cancel. They're not collinear. And what happens is you end up with a residual net force, which I call the ramp force. Ramp force, it's not a fundamental force like gravity or something like that. It's the failed cancellation between support force and weight. And it points remarkably, but not terribly surprisingly, right downhill, perfectly downhill. Not a little up, not a little down, right down the hill. And that's the only force, that is the net force then acting on the wagon. I'm going to take the weight out because it's treacherous to let this guy go with all that weight in it. This guy, when I have my hand on it, there's a third force in the story, and that I'm canceling the ramp force right now. That's my only job, is to pull uphill just enough to cancel the downhill ramp force. When I get my hand out of the story and return to this sort of pristine, simple story, the ramp force is straight downhill. Is that okay? And that's the strength of that ramp force depends on the steepness of the ramp. If the ramp has no steepness, well, then the cancellation becomes perfect, and there's no ramp force. But if I add a little bit of ramp, now there's a little bit of a failed cancellation. There's a little ramp force downhill. Why is it? Oh, there it was sitting on the string, which is enough to gum up its. But there it is. And it accelerates. You notice it doesn't necessarily jump to any specific velocity, but it's accelerating. It's accelerating relatively slowly. If I make the thing steeper, then the ramp force, the cancellation becomes worse still. The ramp force is rather large at this point, and the acceleration is rather large. And in the extreme case of a ramp that's pure vertical, there's no cancellation at all. The support force pretty much goes to zero, and the only force acting on the wagon when I let go is its weight, and down it goes. Full acceleration of gravity. And actually what happens on the ramp then is the wagon accelerates steadily downhill. It's got a constant acceleration just like a falling object, but it's just a smaller downward. It's downhill, and it's a downhill rather than straight down acceleration, but it's less than the acceleration due to gravity, like remember, the acceleration due to gravity is about almost 10 meters per second squared. On this ramp, the acceleration due to gravity is more like 3 or 4 meters per second squared. And it depends on how steep the ramp is. It goes smoothly from no acceleration when this ramp is flat to full acceleration due to gravity when the ramp is vertical, and everything in between. So this is your experience on a bicycle. When you get on a bicycle and you start rolling downhill, or a tricycle, or my son and his cousin experimenting with my mother's wheelchair in the later years of her life on our sloping driveway. And Casey lost control of it while my son was riding it. He was fine, but it was terrifying. Yeah. So all these ramp experiences, rolling downhill, you're accelerating downhill at some fraction of the acceleration due to gravity, depending on how steep it is. And you choose things like, okay, another example. Those of you who've gone downhill skiing, or anything equivalent to downhill skiing, snowboarding, you know why when you come up, you get off the lift and you look over the edge. If the slope is like this, so-called bunny slope, no big deal. The accelerations are modest, right? But if it's like the quadruple diamond, black diamond signal of death, skull and crossbones, it's like that, yeesh, you're just short of falling, right? Almost the full acceleration due to gravity. Okay, so winter sports and all go, or yeah, you can figure this out. Any questions? Oh, yeah. All right, what else? A couple of other useful observations. If I pull uphill on this wagon and I perfectly balance the downhill ramp force, what does that require the wagon? How many think the wagon will be motionless? How many think the wagon will have a constant velocity that might be motionless? Yeah, it's the second. By balancing the downhill ramp force with my own uphill yank, I'm making sure that the wagon's experiencing zero net force. That doesn't mean that the wagon is not moving. It just means that the wagon is not accelerating. Net force is zero. If it was moving, it will continue moving in a straight line at a steady pace. This is an inertial wagon. The forces, not anymore. The forces are complicated, but it's inertial. All right. So the whole story of taking something up or down a wagon, up and down a ramp, is typically when you're conveying something along the ramp, there's a starting process, a coasting intermediate process, and a stopping process. The starting process, you actually have to pull uphill on the thing on the wagon or push it up. This is a grocery cart. You're pushing it up a ramp. To get it started up the ramp, from motionless to moving up the ramp, you have to push uphill harder than the ramp force pushes downhill. The result is the net force is uphill, because you dominate, and the cart accelerates uphill and begins to pick up some speed. You okay with that idea? That's the starting process. The intermediate process, you no longer have to push uphill harder than the ramp force pushes downhill. You just have to balance it. So you back off, you push uphill as hard as the ramp force pushes downhill, and now the net force is zero on the cart, and it coasts uphill. It keeps moving uphill because that's what it was doing. At the top, you want to bring the cart to rest. So now you under-support it. You don't push uphill enough to cancel away the downhill ramp force. You allow the downhill ramp force to win and gradually bring the cart to rest. So this is true of a car. It's true of you bicycling up a hill, all that stuff. Pulling kids up in a wagon, all that. You okay with that idea? The start, coast, stop. All right. Well, that brings me to this. I want to make sure I got to this topic today because this shows up often enough in the problem set, among other things, and it deals with one of the central, most important physical quantities, energy. So having talked about a little how a ramp works in terms of forces and stuff, then well, this question, why is it harder to lift a wagon up than to lower it? Well, because lowering the wagon, of course, you can basically let go, it'll do it by itself. To take the wagon up the hill, you have to invest something in it. It's a process where you're taking something out of yourself and giving it to the wagon to help it rise upward. And what you're giving it is energy, and you're giving the energy by way of a process, a mechanical process known as work. And so to step back for a second and describe these two physical quantities. So energy, it's a word you've heard your whole life. To a physicist, what energy is a conserved quantity in nature. What a conserved quantity is a quantity that has a measurable amount, a specific amount, that cannot be destroyed or created. So my usual analogy is money. Energy and money are very similar. You can't create, on the local scale, we're not talking about governments. You can't create money, you can't destroy it. Again, no counterfeiters and no people who just are so wealthy they can burn money. You basically move it around. And the moving around of money is what makes it interesting. Having it is boring, but being able to do things with it is where it's fun. So energy is similar to conserved quantity. It's truly conserved. There are no ways out of this. I got yet another email a couple days ago, like 3 days ago, from somebody who has invented a way of creating energy. Of course, and he wants my review of his proposal to the Electric Power Research Institute and the Department of Energy. Ain't going to happen. You can't create this stuff. Impossible. So energy is a conserved quantity. It moves between objects. It can take a variety of forms, but you can't make it or destroy it. What else? That's good enough. The fact that it's conserved is what makes it interesting. If it weren't conserved, no physicist would pay much attention to it. So there are very few conserved quantities in nature. Energy's one. We'll hit two more in about a week or so, known as momentum and angular momentum. And then we'll hit one known as electric charge, also a conserved quantity. You can't create it or destroy it. But they're just a handful in nature. So energy is this conserved quantity. It moves between objects. The movement itself is particularly interesting. It moves mechanically by way of a mechanism known as work. And what work is, so there's a circular definition here. Energy is defined officially as the capacity to do work. And work is defined as the mechanical means of moving energy. Well, they're both blaming the other one for their existence. Okay, but energy, we'll see it in action in various places. And work, I'll tell you how it's done. To move energy from something to something else by way of work, the rules are very simple. You have to, for me to do it, I have to exert a force on something, and it has to move a distance in the direction of my force. So, for example, Blocky here. While I'm just holding Blocky, I am pushing up on it, and it is, but I'm not doing any work on it because it's not moving a distance in the direction of my force. To do work on it, I have to push up on it, which I'm doing, and it has to move a distance in the direction of that force. I just did work on it. And now you can start to see where energy is. This thing is much more threatening, certainly to me, and maybe even to you, when it's up high than it was back down here. More about that return in a moment. I've invested in it something that makes it more dangerous. I packed it full of energy. I did work on it, and I increased its energy. This is the vertical version. The horizontal version is similar. If I throw it, I'm not going to throw it. I push it forward to your right as it moves right. I pack it full of energy. So all these cases, force and movement in the direction of the force, they all involve conveying energy to it. So this has got more than it had before. And it's able to do things it couldn't do before. All right. What about lowering it? When I lower it, and I do this essentially at constant velocity to make life simple, which way am I pushing on it? Show me with your hands. It's still upward. I wasn't pulling down. If I pull down, it's going to go real fast, accelerate like crazy. So I was pushing it upward, but it moved in which direction? Moved opposite the force I exerted on it. I did not do positive amount of work on it. I did actually less than no work. I did negative work on it. Work, when you do work on something, you exert a force on it and it moves a distance in the direction of the force. That's a positive amount of work. If it moves a distance in the direction opposite the force, or equivalently, if it moves a negative distance in the direction of the force, that's a negative amount of work. And when you give, and you can do this, you can give negative amount of money to somebody. If you give them positive amount of money, you're conveying money you had to them, right? You do that with green sheets of paper. You can, however, give them less than no money. It's not a typical thing to do, but you give them your mortgage, you give them your auto loan, you give them all these negative amounts, these debts, these negative amounts of money. Your wealth goes up, his goes down, or hers. This is me investing work and doing work and therefore investing energy in this block. This is me taking back that energy. I'm doing positive work on it. I'm doing negative work on it. All right? Well, matter of wording. By default, doing work on something is always a positive amount. It's a convention. So if I say I do work on something, I always mean positive amount, unless I explicitly say otherwise. And, okay, those of you from 1050 know all my old jokes. It's like when you give money to charity, by convention, that's a positive amount of money. If you go and you give the Children's Foundation or something like that, your auto loan, your mortgage, and something like that, you're not a very nice person. All right? So work is always positive unless otherwise. That will come up once in a while. All right, what else? So we'll find cases, just random stuff. If I go and I push on the wall, and let's neglect the fact that the wall will dent a tiny bit. Let's be more concrete here, not in the sense of the material. When I push on this, am I doing any work on it? I'm pushing hard, right? Am I doing any work on the wall? No, because it's not moving. It turns out it's very hard to do work on essentially immovable objects. You have trouble giving them energy. And that is one of the reasons, for example, why balls bounce off of immovable objects pretty well. They try to give away their energy because they carry energy when they're moving. They try to give away the energy, but the surface that can't move can't have work done on it. It can't receive any of the energy. The ball keeps it, and it has to keep going, so it moves as a result. One last point to talk about with work, and then we'll call it a day, a week. That is, if I push the weight up and it moves straight up, of course I do work on it. If I push up and it moves at a cockeyed angle but still rises, I still do positive work on it. But the only part of its movement that counts is the movement along the direction of my force. So the fact that I went up and drifted to the leftward drift didn't count. It was only the upward increase in altitude that counted, because that's the direction I'm pushing, is up. In the extreme case is if I walk around with a block on my shoulder at constant velocity, which way am I pushing on the block? Straight up, right? Stop the story. Which way is it moving? Perfectly horizontally. Those two, my force on it and its movement, are at right angles to each other. I do no work on it. So just carrying something at the details, I got to be a little careful because you got to not speed up or slow down. But if you carry it at constant velocity while supporting it, you do no work on it. You might get tired. I mean, another point. So, but if it's not moving a distance in the direction of your force, if it rises, you do work on it. If it lowers, you do negative work on it. If you just carry it, it's neither. One last thought is just holding the block like this, you of course get tired. And it feels like you're doing a lot of work, but it's work in the generic, everyday language sense. you're not actually conveying any energy to it. It's not changing. You're just getting tired. You're turning your food energy, which is real, into thermal energy, which is also real, but it's all inside you. So it's your own, it's a problem for you, not for the block. All right, have a good weekend, and I'll see you on Monday.